Hello and welcome to the 45th lecture of our course. We have seen several methods in linear algebra to solve the linear systems, and now we are going to look at one very important concept in linear algebra, which is the concept of an eigenvalue and the concept of an eigenvector. So let me start sharing my slides and then we will begin this lecture. Okay, I hope you can see the slides now. So we begin with eigenvalues. Let me just recall the definition of an eigenvalue. So suppose we start with an n by n matrix with real entries, then an eigenvalue of this matrix A is a complex number lambda such that A times some non-zero vector V is lambda times that non-zero vector. So as I told you, I think I may have recalled this definition earlier also. The concept of an eigenvalue requires the notion of that eigenvector. So this vector V will be called the eigenvector. Well, perhaps we should not call it the eigenvector because it's not unique. Any non-zero multiple of this V will again be an eigenvector. So it's an eigenvector. So eigenvalue means that there should be some vector for which your this scalar lambda has the property that A takes V to its multiple by lambda. Okay, then lambda is called an eigenvalue. We know how to determine eigenvalues. The eigenvalues can be determined by solving the characteristic polynomial, which is P lambda, which is determinant of A minus lambda times I. And so once you solve this, you get its roots or its zeros, and those are possible eigenvalues. So once you have such zeros, you will have to look for the vectors for them. And once you have the vector, then the zero will be called the eigenvalue. But the problem here is that computing the determinant is a computationally very expensive thing. And then finding approximations, good approximations, to the roots of that polynomial P lambda is also a difficult thing. So we should look for some better ways. We will perhaps get some approximate solutions, but what we will do is that we will explore other means for approximating the eigenvalues of a matrix. The very first theorem that we encounter in this direction is the Gershgorin theorem. It's a very interesting theorem. Proof is also quite interesting, but we will not be doing the proof in this course. So in the previous slide, we started with a matrix with real entries. However, many times the values, because your polynomial P lambda will be a polynomial with real coefficients. And when you have a polynomial with real coefficients, its roots may be complex numbers. Its roots may be real numbers, or it may be non-real complex numbers. So we start anyway with a complex matrix. We start with this matrix A, which is denoted by Aij. So it's an n by n matrix, and its entries will be A11, A12 dot 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 A1n, A21, A22 dot 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 A2n, and then you will have the last row an1, an2 dot 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 ann. That's how this n by n matrix is written. And once we have this, we define these disks. These are the disks. Disks mean that you have a point and you are taking some certain radius around the point, and you are taking all points within that disk. So you draw a circle around some point, and within the circle you consider all those points. So here we have for each I the diagonal entry, which is the entry AII. Okay, that is the center of our disk, because you are taking all Z which are at some distance, which are less than or equal to some fixed distance from this entry. That means you are fixing this entry AII, you are drawing a circle of some certain radius and then taking all points within that circle. The radius of the circle is given by computing this number, which is the summation of moduli of all non-diagonal entries. Okay, so you are taking the summation of moduli of all non-diagonal entries in that particular row, ith row. You fix a row, take the diagonal element, aii, take all other elements, take their moduli and take the sum of the moduli. You construct a disk with the diagonal element as the center and the radius being the sum that you have obtained. Then once you have these disks, because there are n rows, you will have n disks. Then all eigenvalues of your matrix A are contained in the union of all these disks. So very beautiful theorem, very useful theorem, and the proof is also delightful. Proof is very simple to understand, but you may actually go and look at it sometime, maybe after this course is over. You will have some time to really learn some interesting mathematics and you can look up the proof. Moreover, if there are some disks, suppose that there are k disks with the property that their union does not intersect the remaining n minus k disks. Okay, so you have k disks, there are k many disks whose union does not intersect the remaining disks, then this particular union will contain precisely k eigenvalues. That's the nice thing about this theorem. So in particular, if you have that all the disks are disjoint, then there will be exactly one eigenvalue in each of the disks. Okay, this is what we have in the Gershgorien theorem. It locates the eigenvalues to some extent, and here we don't have to do any difficult computation. We don't have to do any expensive computation. You have to just take the moduli of all non-diagonal entries and sum them up, which is supposed to be the easiest job for a computer. Okay, so for instance, if you take this particular matrix 411 021 minus 209, these are the three rows. Now the first disk will be looking at the first row, take the diagonal entry which is 4 and take the non-diagonal entries, put moduli and take the sum. So that number is 2. And therefore the first disk is obtained by putting 4 at the center and taking the radius to be 2. So it's the complex plane you are looking at. You take the real line and plot the point 4 and you measure the distance 2. So it will start from 2, 4 is the center and then 6 is the end point. That's the interval of length radius 2 from 4, and then take the circle around it. Okay, so that's the disk that you are going to get. For this second row, 2 will be the center and the radius will be equal to 1. So this is mod z minus 2 is equal to 1. So this will start from 1 and it will go up to 3. So these two disks are going to intersect. Okay, but the third disk will have 9 as its center and the radius will be given by 2. So this third disk is somewhat away from the other two disks because this will start from 7 and it will go up to 11, but 7 is not there in any of these two disks. So the union of the first two disks is separate, it is disjoint from the third disk. Therefore, there will be one eigenvalue in the third disk and the two eigenvalues in the union of D1 and D2. So D1 and D2 are disjoint from D3, but they are not disjoint from each other. So we will have to take their union. There are precisely two eigenvalues in D1 union D2, and there is exactly one eigenvalue in D3. We will compute these eigenvalues in one of the tutorial sessions, perhaps, which I will record only for my students. This is how the picture will look like. Let's remember that 4, 2, 2, 1 and 9, 2. These are the three disks. So here we have 4 as the center and then there is a circle of radius 2. There is this 2, 1. So 2 is the center and there is a circle of radius 1. And 9, 2 will tell you that there is this circle with 9 as the center and 2 as the radius. So we see that there is quite some distance between D1 union D2 and D3. Okay, so the Gershgorien's theorem, while it doesn't really tell us what the eigenvalues are, but it tells you where they may be located. And moreover, it has many nice applications. So for instance, if you have that your A is a strictly diagonally row dominant, what it means is that the radius of the circle will be less than or equal to that modulus of the diagonal entry. Okay, this is something that we have already learned, that you put the moduli for all the entries in the ith row, take the diagonal entry separate and take the sum of all other elements, moduli of all other elements. If that sum is still less than the modulus of the diagonal entry, and if this happens for all I, then we say that our matrix A is strictly diagonally row dominant. If you have such a matrix, then Gershgorin's theorem implies that your matrix is invertible, because then 0 cannot be in any of those disks. If your matrix A is not invertible, if the matrix is not invertible, then there has to be some non-zero vector which is made 0 by your matrix. Correct? If every non-zero vector is sent to a non-zero vector, then your matrix is invertible, because then the determinant will be non-zero. Here the determinant is 0, because if A is not invertible, its determinant is 0, and so 0 is a root of the characteristic polynomial, so 0 is an eigenvalue. But if you have this property that summation of mod Aij, where j is different from I, is less than mod Aii, then those disks di, they will not contain 0, because the center has modulus bigger than the radius, right? So if you're looking at your diagonal entry may be 5 and the sum of all other entries may still give you 3. So you will have a circle of radius 3 around 5, and that's not going to contain 0. So any such matrix is invertible, and that would have seemed, if you are just given this property that your matrix is strictly diagonally row dominant, and now prove that it is invertible, that would be a very difficult thing. But once you have Gershgorin's theorem, then proving this is a very, very easy thing. Further, here is a very nice question. If your matrix is strictly diagonally column dominant, that means instead of looking at the rows, we look at the columns and do the same thing. You take the entries in the column, take the moduli, and take the sum of all non-diagonal column entries or under the moduli. If that is less than the modulus of the diagonal column entry, then we say that the matrix is strictly diagonally column dominant. Now, can you say that your matrix is invertible? If your matrix is strictly diagonally column dominant, is it an invertible matrix? The answer is yes. You can use Gershgorin theorem, but not for A. You would use it for A transpose, because if the columns of A become rows of A transpose, and if A is invertible, or instead of putting if first, I will say that A is invertible if and only if A transpose is invertible. So very easy to prove that A transpose is also strictly diagonally row column dominant. Now, when we are actually going to find eigenvalues, most of the techniques would be iterative techniques. We are not going to compute the roots of that characteristic polynomial, because that would be a difficult task, because you will have to first find the characteristic polynomial and then you will have to find its roots. We will look at some other iterative methods, but as always, we will have to start from some initial approximation. And determining regions in which these eigenvalues may lie will be the first step in finding the approximation, because this is where we will start with the initial approximation. So suppose we are given some matrix and we are told that or we can look at its Gershgorin disks, and we realize that there is one eigenvalue whose modulus is bigger than all the other eigenvalues. That such an eigenvalue is called a dominant eigenvalue. Once we know this, then we can try to find that particular eigenvalue by taking the approximations near that, inside that disk. So this is how we will begin. So the methods that we are going to look at, the only method that we will study in this course is called the power method. It's an extremely simple and elegant method. It's a real surprise why this method works many times. The only answer perhaps is that mathematics is beautiful and mathematics is very interesting. It behaves very naturally. Maybe that's the only answer for that. So how do we work with this method? We start with an n by n complex matrix. Okay. We start with this assumption that there is an eigenvalue lambda 1 whose modulus is strictly bigger than all the other moduli of the eigenvalues. This can be verified by looking at the Gershgorin disks, for instance. Okay. So once you have this, the dominant eigenvalue, we will try to compute this dominant eigenvalue. We will make one more assumption. The assumption is that for these other eigenvalues, we have n linearly independent eigenvectors. This is an assumption, it's a serious assumption. But we will make this assumption and we will work with this many times. The power method will work for matrices which do not satisfy this assumption. But whenever the matrix satisfies this assumption, we can prove that the method will work. Other times it may work and sometimes it will not work. Sometimes it may work when this assumption of having n linearly independent eigenvectors is not satisfied. But whenever we have this property, then the method is definitely going to work, and we will actually give the whole algorithm to see how this can be done. So the algorithm consists of choosing some non-zero z in your vector space. So by vector space, I mean the n by 1 column vectors on which your matrix will act. Okay, you choose a non-zero vector. What you do is you compute a power kz. You take various powers of a and apply those powers on z. So you will have z, then you will take az, then you will take a acting on az, then you will take a acting on az. So you will compute these powers acting on z, and finally we will take the limit. So these are vectors in the n-dimensional space, and the limit will give you either the limit will not exist or the limit will be a vector again in the n-dimensional space. In fact, we will prove that the limit does exist in most of the cases, and when it may not exist, or it may actually sometimes the limit may be 0, in that case we will tweak the method slightly so that the limit is, we will change the method slightly so that the limit of that changed method is a non-zero vector. Okay, so let's see why. First of all, this gives us our eigenvalue to begin with. Okay, so we have assumed that there are these n linearly independent eigenvectors v1, v2, vn. These are all linearly independent, and the dimension of your space is also n. You are looking at the n by 1 column vectors. So that dimension is also n. So these n vectors will form a basis for your n-dimensional vector space, and so this z will be a linear combination of your basis elements. So this is, suppose, alpha I vi. Okay, then we are going to apply the a power k to z, but applying a power k to z is simply applying a power k to each of these and then taking the sum of the results. That is what we will have. So this is, moreover, the alpha I being a scalar will come out and you will be applying a power k to vi. But each vi is an eigenvector. So a into vi is lambda I vi. A square in applying to vi will be lambda I square vi. So similarly, a power k applied to each of the v1, v2, vk will give the corresponding kth power, the kth power of the corresponding eigenvalue. So we have lambda 1 power k alpha 1 v1 plus lambda 2 power k alpha 2 v2 plus dot 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 lambda n power k alpha n vn. Here we can take lambda 1 power k constant because you have assumed that it's the dominant eigenvalue. Okay, and therefore it is bigger than 0 definitely. So you can take it constant, divide by the lambda 1 to each of the remaining eigenvalues. Now here this lambda 2 upon lambda 1, this vector has modulus less than 1. Therefore kth power of that will have moduli going to 0. And so as k goes to infinity, lambda 2 upon lambda 1 power k goes to 0. Similarly, lambda n upon lambda 1 goes to 0. So only thing which is left will be this particular alpha 1 v1. So as k goes to infinity, a power kz will converge to lambda 1 power k alpha 1 v1. So for high enough k, the all the other contributions from v2 up to vn will be negligible, and the dominant contribution will be from the dominant eigenvalue. So your a power kz will be very close to this particular lambda 1 power k alpha 1 v1, which is an eigenvector for the value lambda 1. Okay, so you have actually computed an eigenvector, and once you have computed an eigenvector, then finding eigenvalue is easy. You just apply your matrix to that particular vector and see what scalar you get. Okay, so you just compute AV, you know what is your V, so that will tell you what lambda it is for high enough k. Okay, but there is one small problem, which is that your vector z you started with may not have a contribution from v1. You started with a random vector, and this random vector will be perhaps a linear combination of v2, v3, vn. The v1 may not show up there, which is to say that the alpha 1 may be 0. And if alpha 1 is 0, then the limit of this quantity will be 0. We don't want 0 eigenvector. The eigenvector has to be non-zero. So if that happens, we will have to modify. So this is not the tweak to power method that I was talking about earlier. This is a trivial tweak. What happens is that, first of all, whenever you choose your z randomly, then it is likely that your first coefficient alpha 1 is non-zero. If that happens to be 0, then you take the vector subspace generated by the vector you have chosen and choose a vector outside that subspace. Okay, even that may have your first coefficient to be 0. Then take the vector subspace generated by those two vectors and take something outside that subspace generated by them. So there is a linear algebraic result, or there is a linear algebraic trivial reasoning which will say that as you keep doing this, you will reach a stage where alpha 1 is non-zero. So whenever alpha 1 happens to be 0, whenever you see that this limit is going to 0, then you can change your method by choosing a different z. Okay, so that is something that you can do, but rest assured, most of the time the random vector you start with will have the property that its coefficient given by v1, the dominant eigenvalue ka eigenvector, is going to be non-zero. Okay, now so there is one more possibility that your Gershgorin disks may have the property that there is no dominant eigenvalue, meaning there may not be a single disk giving you the dominant eigenvalue, but it might be giving you a single disk giving the smallest eigenvalue. So it may have these kind of properties. You may have that 0 doesn't belong to any of the disks, so your matrix is invertible, and there is a single disk disjoint from all other disks sitting in the smallest part near the 0. Then you have that you have a invert dominant eigenvalue. In that case, you simply work with A inverse. Computing the inverse is not difficult. It's applying Gaussian elimination to a certain number of vectors, right? So computing inverse is not easy. You will have to, it's not difficult. You will have to apply the Gaussian elimination n times, and then you will be able to compute the inverse. You compute the eigenvalues for the inverse. They will be the inverses of these eigenvalues, and then from them you will be able to compute the remaining eigenvalues. Now there is another small problem, and this is where I come to the tweak that I was talking about, that your lambda 1, the dominant eigenvalue, may have the property that its modulus is less than 1. In that case, the kth power of lambda 1 will also go to 0. So you know, we don't want this to be a 0 vector, right? We don't want it to be a very small vector. But that may happen if your lambda 1 has the possibility that its modulus is less than 1. You may have small Gershgorin disks and all may be contained in the interval 0 to 1. That may happen. So your dominant eigenvalue, which will be dominant compared to all other eigenvalues, will still not be big enough to be bigger than 1. Okay, in that case, your lambda 1 power k will go to 0. Another possibility is that your lambda 1 might be bigger than 1 and in the modulus, and then lambda 1 power k will shoot to infinity. So you might get a very big vector. You will get a vector with big moduli, big entries. Then this is what is called an underflow or an overflow. So we want to change our method slightly so that this situation is avoided. So what we do is that we will scale this a power kz at each time so that the limit that we get is a finite quantity and it is a non-zero vector. Yet at the same time, always it will remain an eigenvector for you. The limit will give you an eigenvector for the dominant eigenvalue. So this is what we want to do. Now listen very carefully. The method that I am going to outline is very simple. There are some small changes that we have to do, some numbers that we will have to compute, but using those things we can go and find these eigenvalues. So what we do is that simple thing. You start with your beginning vector to be a vector of unit norm. You make sure that your vector has supremum norm or the infinity norm equal to 1. Okay. So that means that the maximal entry in the moduli of your vector is equal to 1. Once you have that, you choose that particular component where the entry is 1. And we call that component to be P naught. So we started with a vector Z naught, which is a vector of unit norm. So one of its entries must be equal to modulus being equal to 1 and all other entries will have modulus less than or equal to 1. So you choose that one whose modulus is equal to 1. We call it Z naught P naught. It's the P naught component of the vector Z naught. Okay. Apply the matrix A to Z naught. Now Z naught had unit norm, but there is no reason to believe that W1, which is the A applied to Z naught, will have unit norm. So we will have to get another vector Z1 from this W1. And it's quite clear how to get this vector Z1 because you will simply divide by the norm of W1. But before going to do that, we will define mu1, which is a scalar, to be the P naught entry, P naught component of the resulting vector W1. Okay, so let me repeat the whole thing. We started with a unit norm vector and we took a component whose value in the modulus is 1. Apply the matrix A to it and then see the value of that particular component. We call it mu1. This mu1 has the property that since it is W P naught of 1, it's also equal to, I should put a modulus here because the modulus of Z P naught is 1. It's equal to W P naught 1 upon mod W Z P naught 0. Right? Because the modulus is equal to 1. So instead of saying that the vector is W P naught 1, we write it as W P naught 1 upon 1, and that is simply Z P naught naught. That's the norm. Now, we had assumed that our vector Z naught is a linear combination of eigenvectors, right? So this was assumed to be of the form alpha 1 V1 plus dot 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 alpha n Vn, and we took the P naught component. So we had these vectors V1 up to Vn. These are the column vectors. Their linear combination gives us the vector Z. Then if you wanted to find a particular component in Z naught, you have to simply look at the particular component in all those vectors. So taking the P naught component will give you this. Z P naught is alpha 1 V1 sub P naught dot 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 alpha 1 alpha n Vn sub P naught. The P naught is the component of the vector Vn. Here P naught is the component of the vector v1. We are simply taking those components, and once you have applied the vector capital A, the matrix capital A, you get W1, and but you are still taking P0. So mu1 will be, I need to put a modulus for the denominator. So there will be a modulus here in the denominator. But we observe that these lambda 1 and lambda n have come in the numerator. That is because you have applied A to the vector z0, which is to say that you have applied A here to the right hand side, alpha 1 v1 up to alpha n vn, and that is same thing as applying the matrix A to each of the v1, v2, vn, which will give you the eigenvalues lambda 1 up to lambda n. Okay, so this is what your mu1 looks like, and if I now take lambda 1 constant out, we will see that the numerator has lambda n upon lambda 1 for the nth component. The first component will have no lambda 1 because that is taken common. The second will have lambda 2 by lambda 1, and so on. So this is the property of mu1, that it is lambda 1 times some complex number. Okay. Let's go to the next stage. Now we have chosen. So once you have this vector w1, we choose the least integer w1 p1, whose modulus is the norm of this vector, and you divide by that particular complex number, so that you will get z1 equal to 1 upon this particular vector into the vector w1. So we have simply divided by that non-zero value, so that the quotient will have maximum value to be equal to 1. You have simply taken, this is the infinity norm. So you have taken that particular component whose value in the modulus is biggest in that vector w1, and you have divided by that. So after having divided by that, the maximum value of the divided vector is now equal to 1, and therefore you have this vector z1, which is of infinity norm 1. Okay, so we will then repeat the process for this z1 and continue. What we will have at the end is that once you have zm minus 1, which is of infinity norm 1, and pm minus 1 is the least integer whose modulus is equal to 1, then we define wm to be a times this m minus 1th vector, and the mu m will be obtained by choosing the previous one under it. So here, for instance, mu1 was w p naught upon z p naught. Here this would be w p m minus 1 upon z p m minus 1. That would be equal to 1 because the p m minus 1 is the least integer, with this being equal to 1, right? So we will be dividing by this particular modulus. So having done this particular z m minus 1 p m minus 1 will have the property that in the denominator you will have lambda 1 power m minus 1 alpha 1 v1, lambda 2 power m minus 1 alpha 2 v2 dot lambda n power m minus 1 lambda n vn. That's how the zm minus 1 will look like. And in the numerator you will have lambda 1 power m alpha 1 v1, lambda 2 power m alpha 2 v2 up to lambda n power m alpha n vn. So taking lambda 1 power n common from the numerator and lambda 1 power m minus 1 common from the denominator will give you lambda 1, a single lambda 1 outside. The remaining entries in the numerator will have mth power of the quotient lambda I upon lambda 1, and the denominator will have m minus 1th power of lambda I upon lambda 1. The first entry will remain the same for both the numerator and denominator. So when you let this m go to infinity, these entries are going to go to 0. What you will have is that the numerator will have entry equal to the entry in the denominator, assuming of course that your alpha 1 is non-zero. You will have that this entry cancels out and your mu m will converge to the lambda, the eigenvalue lambda 1 you are looking at. So here you don't even have to compute that lambda as the difference or the ratio of the vector v as vis-a-vis the vector av. This is what we are going to get. So once we have this, the modulus of each zi is equal to 1. Therefore, there is no chance that those vectors will go to 0. The modulus is equal to 1. Therefore, the limit exists. This is one very beautiful fact from mathematics, that the set is closed and bounded. So any infinite set should have a limit point, and the limit will exist. And moreover, these mu n's that you were looking at, that will converge to the eigenvalue lambda 1. This is what we have. So let me just give you an example. We will not be able to do this example in great detail here in this lecture, but I will give you some of the main steps. This is the matrix, 2 by 2 matrix, and the eigenvalues are 4 and 1. Let's start with the vector 1 comma 1, which is a vector of modulus 1, infinite norm 1. A acting on this will give you -5 and 13. You have to just sum the entries in each row. And A square will give you this entry. And finally, A power 6 will give you this entry. So, of course, the first entry diagonal, the dominant eigenvalue is 4. So, the higher powers will have bigger and bigger entries. So, we have to scale these. And we observe that the norm of A z0 is 13. The norm of A square z0 is 61. So we will have to be looking at 61 upon 13, then the norm of the next one upon the norm of the previous one, and so on. So the approximations to the dominant eigenvalue are 61 by 13, which is the norm of the second one upon norm of the first one, and the norm of the third one upon norm of the second one, so on up to the sixth one, whose norm is 16,381. The norm of A power 6 is 16,381, and I did not tell you what the A power 5 was, but trust me that its norm is 4093. So this ratio is almost equal to 4. So our method has worked beautifully. Already in the sixth power, we are getting a very good approximation to our eigenvalue. And if you were to take the norm 1 vector parallel to that sixth vector that we had, we see that it's equal to -12 and 1 roughly. So actually -1 and 2 is an eigenvector for the eigenvalue 4. And if you want to take something which is parallel to this but with norm equal to 1, then you will have to divide it by 2, and so you get -1 by 2 and 1. These are the entries of the column vector, which gives you a norm 1 vector which is parallel to your eigenvector, almost. Okay, so this is almost an eigenvector for A with eigenvalue 4. Okay, and once you have found this dominant eigenvalue, you would want to know how to find the remaining eigenvalues. So suppose the matrix A is found. I am well aware that I may be going beyond time even in this lecture, but stick with me for one more slide. So suppose A is a matrix and you have found this particular eigenvector with the eigenvalue lambda sufficiently accurately. Then what you do is that you use Gram-Schmidt orthonormalization, which is that you start with your vector V, choose any basis consisting V as your first vector, and apply Gram-Schmidt orthonormalization. So what it does is that it will keep giving you other basis elements which will be orthogonal to the vector V you started with. So in particular, when you write the matrix capital A with respect to this basis, you will get a matrix of this particular form. It will have the first entry to be lambda 0, 0, 0, because your small v is an eigenvector. Okay, and the remaining part will be an n-1 by n-1 block. The remaining part in the first column is 0, and there will be some entries perhaps in the first row. So I am quite sure that you would have done your linear algebra course, and Gram-Schmidt orthonormalization would also have been done. But if it is not very clear to you, we will do an example of this in our tutorials. and this will then be clear. But once you have done this kind of breaking your matrix into smaller matrices, then the eigenvalues of the matrix are lambda and the eigenvalues of this n-1 by n-1 block. So then that's how we will proceed with the, then you will again look at the Gershgorian disks for the remaining n-1 by n-1 matrix and find the dominant eigenvalues using the power method for that particular one. This is how the whole thing takes place. And of course, what next would be a very good question. There are so many things that one can learn in this beautiful course in numerical analysis, but all good things must come to an end. And even if there are several things, that process never stops. The learning never stops. A course may end, but the learning never ends. So this is where we complete our syllabus. I would like to express my appreciation for the TAs, both the graders, which are the PGTAs, and the UGTAs who have been taking tutorials, and they also completed gradings for the various quizzes. I would also like to thank all my students who have stuck patiently with me. So thanks a lot to all of you, and this is where we end our course. Good luck to your examinations, and see you soon in person, hopefully. Thank you.